Good afternoon friends, and welcome again once more to another edition of Parijat Sir classes. And today I would be starting with you another session of physics class 12, and the topic for today will be magnetic field due to current. This is the topic which we are going to study, physics class 12, and this is the topic which we are going to study, that is magnetic field due to current. Okay, so let's get started with the topic. So see, first of all I want to explain to you that whatever we are discussing here is the complete theory. This is the complete theory of the class 12 of this chapter, full complete theory. You don't have to make any notes, no notes. You don't have to make any notes of it. This complete theory and concepts are discussed in this chapter. So if you read and study this chapter properly, you don't have to make any notes of your own. You don't have to make notes, just follow the discussions which I am explaining here. Okay, so please keep following and please keep watching Parijat Sir classes. And like, share and subscribe my channel. Okay, so that is a huge motivation for me. So let's get started with the topic. So the topic for magnetic field due to the current. Okay, so first of all, see what we are going to study here. See, we are discussing only the very important points and notes and then concepts which you will be dealing in this chapter. First of all, it is Ampere's swimming rule. So let us discuss what is Ampere's swimming rule. So as you can see here, that here is a wire, AB is a wire which is in which the current is flowing in this direction. As you can see, current is flowing in this direction. Okay, this is the battery whose positive terminal is this side and negative terminal is this side. So current is flowing like this through the wire AB, correct? So now here is a compass needle. As you can see, we have placed a compass needle. This is the north pole and this is the south pole. We have placed a compass needle, north pole and a south pole. So we see that whenever there is a current flowing through this, there is a motion. There is a motion. So watch here. Suppose the motion of the north pole is towards this side. Now if we reverse the direction of the current, you see the north pole will move away. The north pole will move away. Okay, so how to find the direction of this motion when current is flowing through the wire AB? How to find the direction of this motion? So based on that, Ampere's swimming rule is our point of discussion here, because it tells us how to find the direction of this motion. So if we imagine a man swimming along the wire, so suppose the man is swimming like this. Suppose the man is swimming like this. This is the man. This is the man. Okay, along the wire in the direction of the current. That means the man is also swimming like this. The man is also swimming in the direction of the current with his face towards the needle. With his face towards the needle, so that the current is entering through his feet. So how is the current entering? The current is entering through his feet and leaving through his head. Okay, then the north pole of the magnetic needle will be deflected towards his left hand. So where is his left hand? Here is his left hand and here is his right hand. So the north pole will shift towards his left hand. North pole will shift towards his left hand. So this is the Ampere swimming rule. Okay, the north pole will be shifted towards the left hand. As you can see, the left hand of the man will be this side and the right hand will be on this side. So if the current is entering like this through his feet and leaving through his head, the north pole will move towards the left hand, clear? So now if the current is flowing like this, his left hand was here, his left hand will be here, and the right hand was here. Now current is entering through his head and leaving through his feet. So it is, the needle will move towards his right hand. The needle will be moving towards his right hand. So that is the concept. Okay. Now what is snow rule? Snow rule that current enters from the south to north. So this is the south and this is the north. So if the current enters from south to north over the needle, see the wire is above the needle, then the north pole moves towards the west. So this is your west and this is your south. So the north pole will move towards the west. Clear? So if the snow rule says that if the current enters from south pole to north pole, the north pole will move towards the west. Clear? So this is the snow rule. Now magnetic field. What is magnetic field? The space around a conductor carrying current in which magnetic effect can be felt is called magnetic field. That means, why is this needle moving? Because there is a magnetic field surrounding the current along the wire. Okay, why is the needle moving? Because there is a magnetic field around the wire. Magnetic field around the wire. That is why the needle is moving. The magnetic field vanishes as soon as the current is switched off. So remember it, when we switch off the current, the magnetic field will be vanished and the charge stops moving. Now current is proportional to the charge. If the current is 0, if we stop the current, that means there is no charge flowing. So also if we stop the flow of charges, then the magnetic field will be vanished. So thus a moving charge, this is an important thing, thus a moving charge is the source of both electric and magnetic field. Okay, magnetic field is denoted by B. Please remember this, magnetic field is by B. So if there is a moving charge, it can create both electric and magnetic field. If there is a moving charge, then it can create both electric and magnetic field. You have to note all these points very, very carefully. So that means you should have a moving charge. You should have a moving charge to create magnetic and electric field both. So the symbol of magnetic field is B and it is a vector quantity. Magnetic field is a vector quantity because it depends on the direction of motion. Okay, it depends on the direction of the current. So please remember that magnetic field is a vector quantity. Force on a charge. Now we are going to study force on a charge moving in a magnetic field. So watch here. Suppose this is the magnetic field's direction. Please see, this is the magnetic field's direction. Okay, and suppose here is a charge moving, this is a charge moving which is making an angle theta, with the direction of the magnetic field, which is making an angle theta. See, it is moving with a velocity v. Okay, this is the magnetic field, this is the charge moving, making an angle theta with the direction of the magnetic field with a velocity v. So this v can have two components. One is v cos theta, one is v sin theta. One is v cos theta, which is along the magnetic field. One is v sin theta, which is perpendicular to the magnetic field. So remember it, the force acting on the charge should be proportional to the velocity to the charge. Okay, so force acting on the charge is proportional to the charge. Force acting on the charge is proportional to the perpendicular component of the velocity. okay, and force acting on the charge will be proportional to the magnetic field. So if I combine all of them, we get the force is proportional to q VB sine theta, and to remove the proportional we use the value k. Now if k is 1, then the force acting on the charge q which is moving, there is a charge q which is moving with a velocity v in a magnetic field b. So what is the force acting? This is the force acting on the charge moving in a magnetic field with a velocity v. Clear? So next, so this is that is the first formula what we have studied. So this is our first formula which we have studied. So first let us see if anyhow we can highlight this. So this is our first formula which we have studied. So please remember it. This is the force acting on the charge moving in a magnetic field. Clear? So now let us see the next thing, which is, now see here, since it was F equal to q VB, and we know that if it is a sine theta, then the product will be written in the vector form, V cross B. Product is written in the vector form. Now watch here, the direction of F is found by the right hand screw rule. The direction of F is found with the help of the right hand screw rule. Please remember this, the direction of F is found by the right hand screw rule. So remember it, direction of force on positive charge is upward. Please remember here, force on positive charge is upward, and direction of force on negative charge is downward. So please watch here, direction of force on positive charge is upward and direction of force on the negative charge is downward. So see here, this is the magnetic field, this is the charge moving with a velocity v at an angle theta. So this is a positive charge. Please watch here, positive charge. So direction force is up. And if this is a negative charge, if this is the negative charge, this is the negative charge and this is the positive charge. So the direction of force will be down. Direction of force will be down. So let us study some special cases here. If theta is 0, if theta is 0 degree or 180 degree, that means what? The force, the charge is moving. Suppose this is the direction of the magnetic field and the charge is also moving in this direction. So theta is 0 degree. Or the charge is moving opposite to the magnetic field. So theta will be 180 degree. So in that case what will happen? Sine 0 and sine 180 is sine 0 and sine 180 is 0. So the force acting in that case when the charge is moving in the direction of the magnetic field or opposite, remember it, the force acting should be 0. The force acting will be 0 if theta is 0 degree or 180 degree. The force acting on the charge will be 0 degree, 0. Okay, no force will act on the charge. Similarly, so here please remember it, no force, the field does not experience any force, no force will be acting on the charge. Similarly, if V is 0, please watch here, if V is 0 here, so we can say one thing, that is, if V is 0, that means if the charge is stationary, so F will be 0. If V is 0, the F will be 0. Clear? That means the charge particle will be at rest and no force will be acting on it. That means force can act only on moving charges. Similarly, if theta is 90 degree, that means the charge is moving perpendicular. The force acting will be maximum force. This is the maximum force acting on the charge only when the theta is 90 degree. That means when the charge is moving perpendicularly, to the magnetic field, it experiences a maximum force. Okay, and remember it, the direction of force is determined by Fleming's left hand rule. The direction of force is determined by Fleming's left hand rule. Please keep this in mind. The direction of force is determined by the Fleming's left hand rule. So what is the Fleming's left hand rule? Let me tell you. Fleming's left hand rule. Please watch here. This is your left hand. Fleming's left hand rule. So it tells that the middle finger is the direction. This is the middle finger. It is the direction of velocity. The forefinger is the direction of the magnetic field. So the thumb will point to the direction of the force. The thumb will point to the direction of force. That means you have to keep all these three fingers perpendicular to each other. All these three fingers should be perpendicular to each other. Then if the forefinger points to the direction of magnetic field, the middle finger points to the direction of velocity, then the thumb will point in the direction of the force. This is the Fleming's left hand rule. Okay. Second is, what is the SI unit of magnetic field? SI unit of magnetic field is Tesla or Weber per square meter or Newton second per coulomb per meter. Please keep note of these. These are very, very important. Keep note on these. Next, dimension of magnetic field. You can have a note of this. M a to the power minus a is ampere, a is ampere, t is the time. A is the ampere, t is the time. Next, we are dealing with a very important thing, that is Biot Savart law. Biot Savart law, very, very important topic. So what does Biot Savart law? It deals with magnetic induction at a point due to a small current. Remember it, small current element. Due to a small current element, we will be taking a small element, small length, and due to that small length, what is the magnetic induction? Please keep note here that in the case of Biot Savart law, we deal with magnetic induction. Remember it, we deal with magnetic induction. Clear? So let's now see. Suppose this is a wire. Please watch here. This is a wire which is carrying the current I. Let us take small element. I told you Biot Savart law deals with very small current element. So let us cut a small current element AB of length DL. So see, this is the length DL, small element of length DL through which current is passing. I want to find out at a distance of R at this point P, which is making an angle theta, what is the magnetic field here? What is the magnetic field here due to this current element DL carrying current I at a distance R making angle theta? So please remember that magnetic field depends on the strength of the current you are passing. Number two, it will depend upon how much length of the element you have chosen. It will depend upon the sign of the angle. Sign of the angle, the distance vector and the current element is making. Please remember this angle. So magnetic field is also depending upon the sign of the angle between the wire and the displacement vector R. And magnetic field is also inversely proportional to the square of the distance R. So combining all of these, we get this is I dl sine theta by r square. If I combine all these factors, I will get this. Removing the proportional, I will write it as k, where k is actually mu 0 by 4 pi. K is a constant which is mu 0 by 4 pi. The value of mu 0 is 4 pi into 10 to the power minus 7. Please remember it, 4 pi into 10 to the power minus 7 Weber per ampere per meter. So if I put it, the magnetic field here, I can write it dB will be equal to mu 0 by 4 pi I dl sine theta by r square. This is what we are getting. Okay, and please remember the direction of the magnetic field. The direction of magnetic field is found by right hand screw rule. The direction of the magnetic field is found by right hand screw rule. Very, very important. Right hand screw rule. The direction of magnetic field is found by the right hand screw rule. Okay. So this is the magnetic field due to the small current element. This is the magnetic field due to the small current element dl. So for the whole wire, if I take, so I will integrate this, integrate the magnetic field. Clear? So see, mu 0 by 4 pi I r square sine theta, these all are constant and will go out. Clear? And will go out. So here what we can write is that this is mu 0 by 4 pi I dl sine theta by r square. If I integrate this, I will get the magnetic field due to the whole wire. Due to the whole wire, I will get the magnetic field due to the whole wire. So if we write it in terms of Q and V, so please note this formula. Magnetic field expression in terms of Q and V. That means not in terms of I, but in terms of Q and V. Now this is very important. Magnetizing force. Please remember that was magnetic field, and now we want to find out the magnetizing force. Okay, or magnetic intensity. Please note this, magnetic intensity. How do we find out? It is B by mu 0. So we already found the B, so it is B by mu 0, and so we can easily see that this is another formula. This is another formula. H equal to B by mu 0. H is the magnetic intensity. H is the magnetic intensity. Clear? Let's move on to the next thing. Some characteristics of Biot Savart law. Very, very important characteristics of the Biot Savart law. So this is, we are doing the characteristics of Biot Savart law. Clear? So let us discuss one by one here. First, it is valid for symmetrical current distribution. Very important. Symmetrical current distribution, very, very important. That means the current distribution should be like this. For example, you cannot take an irregular shape. You have to take a regular shape. You have to take the current should pass like this. It should be symmetrical. You can take a sphere. It should be symmetrical. It should be symmetrical. Okay, it should be symmetrical. Cone. It should be a symmetrical. Current should pass like this. Current should be passing through those figures which are symmetrical. Current distribution should be symmetrical. So please keep note on these. So remember it, Biot Savart law is used only for symmetrical current distribution. Clear? Next is applicable only to very small lengths of conductor, very small lengths of conductors. Third, the direction of dB is perpendicular to both IDL and R. That means this is the IDL part, this is the current flowing, and this is the DL which is carrying the current, and this is the R, so they should be 90 degree R. So here I have to find the magnetic field at this point. So the direction of dB is perpendicular to both IDL. So remember it, the direction of the magnetic field, the direction of the magnetic field should be this is the direction of magnetic field is perpendicular both R, and it should be perpendicular to both the IDL. That means B is perpendicular to IDL and B is perpendicular to R. Please note that. Okay. Next is, if theta equal to 0 or 180 degree, that is, the point is lying on the axis of the conductor carrying current, dB is 0. Please remember it. If the point P is lying on the axis of the conductor carrying current, that means if I take it like this, that this point P lies anywhere on this line, anywhere on this line. If the point P lies anywhere on this line, then the magnetic field acting on it will be 0. No magnetic field will act on it. Okay. Fifth, if theta equal to 90 degree, that is, the point P is lying perpendicularly. See, if theta is 90 degree, suppose this is 90 degree, if theta is 90 degree, then remember it that the magnetic field induction is maximum. B will be maximum. Clear? Next is similarities between Biot Savart law and Coulomb's law. Similarities between Biot Savart law and Coulomb's law. So let us see what are the similarities. In both laws, the field at a distance varies inversely as the square. Okay. In Coulomb's law also, field is proportional to 1 by r square. In Biot Savart law also, field is proportional to 1 by r square. Clear? Both obey superposition principle. That means F net force will be the force due to all the charges, first charge, second charge, in this way. Similarly, the magnetic field net should be the magnetic field due to flowing of the first current. Suppose there are many currents flowing, so magnetic field due to the second current, and in this way. So this is called superposition principle. Both magnetic field and electric field are linear. Please watch here, they are linear. Okay. Next is, so these were the similarities. Now is the difference between Biot Savart law and Coulomb's law. So this is important. Biot Savart law and Coulomb's law. What is the difference between them? First, electric field is produced by a scalar source. Electric field is produced due to a scalar force. This is the electric field. 1 by 4 pi epsilon O Q1 Q. This is Q by R square. Okay. So this charge is actually a scalar. Charge is always a scalar. But in the case of the magnetic field is produced by a vector source, which is the current. Magnetic field is due to the current element IDL, which is a vector source. The electric field is acting along the line joining the Q and the point. Mind it, it is along the line and it is perpendicular. Magnetic field will be perpendicular to both IDL and R, but electric field will be along the line joining the charges. Biot Savart law is dependent on the angle, but Coulomb's law is independent of the angle. So Biot Savart law is dependent on the angle. So that means I can easily tell B proportional to sine theta. But Coulomb's law will be independent of the angle. Clear? Let's see the next one. Magnetic field. Now we are dealing with magnetic field due to a straight conductor carrying current. So see, this is the conductor. This is the conductor which is carrying current. XY is our conductor. XY is our conductor. It is carrying current I. This is the carrying current I. This is the current which is flowing from X to Y. I want to find out what is the magnetic field due to this element DL at a distance of R, making an angle theta. Here I want to find out what is the magnetic field. Here I want to find out what is the magnetic field. So let's see how it is being done. Okay, so first of all, see, let us choose a current element DL making an angle theta at a point P, distance R. Suppose this is the length L and this is the distance A, perpendicular distance A. Okay, so as you can always see here that R square is actually L square plus A square. We can see this. Okay, so due to the current element DL which is carrying current I, the magnetic field at P is given as, due to this formula according to Biot Savart law. We have already done that. Biot Savart law says that this is the magnetic field at a distance of R. Now please watch here, this angle is phi. As you can watch here, this angle is phi. Suppose this angle is phi 1 and this angle is phi 2. Clear? Phi 1 and phi 2. Okay, so we can easily say that theta plus phi is equal to 90 degree. Please watch here, theta, this is 90 degree. So theta plus phi equal to 90 degree, or theta equal to 90 degree minus phi. So sine theta will be sine 90 minus phi, which is cos phi. And what is cos phi? Please watch here. What is cos phi? Let me rub these. So what is cos phi? As you can see from the figure, cos phi will be base by hypotenuse, which is A by R, cos phi, or R is this, and tan phi is L by A. See, tan of phi, this is my phi, perpendicular by the base, tan phi, or L equal to A tan phi. Okay, so differentiating it, we will get DL equal to A sec square phi d phi. Please see, differentiated, we have differentiated it. Now let us put one by one in the formula. So dV mu 0 by 4 pi I dl, this is the dl. Instead of dl, we'll put A sec square phi d phi. Instead of sine theta, we have put cos theta, cos phi. And instead of r square, we will put A square by cos square phi. So which is mu 0 by 4 pi I by A cos phi d phi. So now watch here, current is going like this, so the direction of the magnetic field will be perpendicular into the paper. it is perpendicular into the paper. Please watch one thing. This sign means perpendicular into the paper, perpendicular into the paper, okay, and this sign means perpendicularly out of the paper, perpendicularly out of the paper. So please watch here. And since we are using right hand screw rule, so the magnetic field current is going up, so the magnetic field according to right hand screw rule will go down perpendicularly into the paper, perpendicularly into the paper. Clear? So that is why perpendicularly inward. This magnetic field is perpendicularly into the paper. Now this was due to the length dl. So magnetic field due to the whole wire will be, see, the angle from this extreme end to this extreme end changes from phi 1 to phi 2, okay, and because it is below the line, so it is minus phi 1 to phi 2. So these parts are constant, they will go out. So cos phi is sin phi, integration of cos phi is sin phi, phi 2 and minus phi 1. So putting it, we get this formula. So this is the magnetic field due to a straight current carrying conductor. Please note, this is the magnetic field due to the straight current carrying conductor. Very, very important formula. Please keep this in mind. Where phi 1 and phi 2 are the angles made by the extreme ends of the wire. Phi 1 and phi 2 are the angles made by the extreme points of the wire. Clear? Let's see now special cases. Let's see the special cases. What will happen here? Okay, so first of all, when the conductor is infinite length, that means very, very big length, please note phi 1 and phi 2 will be 90 degree. Infinite conductor, phi 1 and phi 2 will be taken as 90 degree. Clear? So now putting it in that formula, we get this is the magnetic field due to an infinite wire carrying current. Please watch it. Magnetic field due to an infinite wire carrying current, okay, at a distance of a, at a distance of a. Magnetic field due to an infinite wire carrying current at a distance of a. Second case, this was the first case. Second case, when the conductor is infinite length and the point P lies near X or Y, that means P will be either near X, P will be either here or here or here, okay, P will be either here or here. In that case, what is the magnetic field? So please note that if it is near X, phi 1 is 0 and phi 1 is 90 degree. If it is near X, phi 1 is 90 degree. If it is near, and phi 2 will be 0 degree. So putting it this, so we get that if the point lies on any end, any one end, mu 0 I by 4 pi a, mu 0 I by 4 pi a, and this is magnetic field due to a straight wire carrying current, infinite wire. That means you have the wire like this. This is a wire, infinite length, carrying current I, okay, at a distance perpendicular a, magnetic field here. What is the magnetic field? I will find, that is, this is the formula. Clear? And if P is anywhere here, suppose this is P is here, P is here, so what is the magnetic field? This is the magnetic field. Third, if the point P lies on the conductor, please note theta will be 0 and phi 1 and phi 2 will also be 0. If the point P lies on the conductor, theta, phi 1, phi 2 all are 0, and in that case the magnetic field will be 0. Please note that. If the point P lies on the conductor, the magnetic field is 0. Next is direction of magnetic field is found by the right hand thumb rule and Maxwell's corkscrew rule. Please, sometimes they ask you how will the direction of the magnetic field will be found. So as you can see here, this is the right hand thumb rule. Right hand thumb rule says hold the wire carrying current on your right hand. Hold the wire carrying current on your right hand. Place the thumb in the direction of the current. So the direction in which your fingers will curl is the direction of the magnetic field. Now see here, the magnetic field is like this, and here the magnetic field will be like this. This is the right hand thumb rule. Corkscrew rule, Maxwell's corkscrew rule says that keep moving your finger like this. Okay, so your direction of the thumb is in the direction of the current. So the direction of the fingers is giving you the direction of the magnetic field. Okay, so if the current is flowing like this, make your corkscrew move like this. So see, this is how you will be turning, and you can easily get the magnetic field. Clear? Next is so let's see the next part. Magnetic field at the center of the circular coil carrying current. Magnetic field at the center of the circular coil carrying current. So see here, this is a circular coil which is carrying current. Current is entering and leaving. I want to find out what is the magnetic field at the center. Okay, so for that, choose a small element dl at a distance of r, okay, making 90 degree. What is the magnetic field due to this? As a magnetic field here, current is going like this. So using the right hand rule, the magnetic field's direction will be into the paper. Clear? Will be into the paper. So this is according to Biot Savart law. This is the magnetic field due to a small current element. Now here theta equal to 90 degrees, so it is sin theta 1. So this is the formula. Now total magnetic field at the center will be the integration of this. So if I integrate this, take out the constants. So these are the constants. Integration of dl. Integration of dl means take the whole length, which is 2 pi r. Okay, dl means the whole length, and it is a circle, so total length will be 2 pi r. So this is from here the things cut, and this is the magnetic field due to the circular wire carrying current at the center. This is the magnetic field due to a circular wire carrying current at the center. Now if you give n turns, if suppose there are n turns, means like this, if you make turns here, okay, n turns, so the magnetic field will be what? It is just multiply this with n. So this is the magnetic field due to a circular wire carrying current having n turns. Magnetic field due to a, now here please watch one thing, magnetic field due to, so this is what, this is due to the whole wire at the center. Now if I take a part of the wire, for example, if I take like this, if I take the wire like this, making an angle alpha, okay, and carrying current I. So what is the magnetic field at this point? What is the magnetic field at this point? It is this formula, mu 0 I n by 4 pi r into alpha. Please note here, the magnetic field at the center will be this, where alpha is in radians. This is the angle alpha, and that alpha should be in radians. Example, suppose it makes 60 degree, so we have to take it as pi by 3. Suppose it makes 30 degree, so it is pi by 6, like this. So we have to convert it to radians. So this alpha should be in radians. Okay, so using this formula we can find out what is the magnetic field at the center due to the circular wire which is making an angle alpha. Clear? So friends, next see, 1 minute. Okay, so friends, next see the general rule to find the magnetic field due to a circular coil carrying current. So please watch here, very important, very important. If the current flows in a clockwise direction, if the current is flowing in a clockwise direction, please note this, the magnetic field is into the paper. And if the current flows in anti-clockwise direction, the magnetic field is out of the paper. That means, if I show you, if the current is flowing like this, clockwise, then the magnetic field will be into the paper. That means this. And if the current is flowing anti-clockwise direction, then the magnetic field will be out of the paper. Magnetic field will be out of the paper. Clear? Now we want to find out the magnetic field. We want to find out the magnetic field on the axis of a circular coil carrying current. On the axis of a circular coil. So please watch here. This is the circular coil. This is a circular coil. This is a circular coil, and I want to find the carrying current I. So as you can see, okay, the radius is A, and I want to find out what is the magnetic field due to this wire at the point P. I want to find out what is the magnetic field due to the wire at a distance x. At P, what is the magnetic field due to this whole circular wire? Clear? So let us do this now. So first of all, see friends, what we will do, please watch here. Let us imagine that we have taken a small current element dl here. The current is flowing, we have taken a small current element dl. Okay, and due to this dl, first I want to find out what is the magnetic field at a distance r. What is the magnetic field at a distance r? I want to find out. So what is r? R is this. This is our r. And according to Biot Savart law, magnetic field due to a current element is given like this, where the theta, now this is acting as a tangent, so this is 90 degree. This is 90 degree, so I can tell that sine 90. So this is the magnetic field due to that current element. This is the magnetic field due to the current element. Clear? So now here what we will do is that, please note that magnetic field at P due to ideal at D. So watch here, this is again, we take a magnetic field here, we take a current element here, ideal. So at due to the DL part, what is the magnetic field again at the distance R? So it will be in this direction, it will be in this direction. Suppose this makes a phi. Now we know magnetic field is always perpendicular. Magnetic field should always be perpendicular into the paper. Clear? So if this is phi, this angle is also phi. Let me clear out. If this is phi, this is phi. So there are the two components of the magnetic field, as you can see, is dB sin phi. This is one component, dB sin phi, and dB cos phi. Similarly, due to the lower part, there is again dB sin phi and dB cos phi. Now this dB cos phi will cancel each other. So due to the opposite DLs, the magnetic field at the center will be summation of this dB sin phi. Okay, so if I can take it like this, the magnetic field, so as we are seeing that the horizontal components are dB sin phi and vertical components are dB cos phi. So magnetic field due to the opposite components at P will be the sum of only the dB sin phi, because all dB cos phi will cancel out. All dB cos phi will cancel out. Only the dB sin phi will get added. So total magnetic field at P due to the whole coil will be integration of all the dB sin phi. Now if I take this in there, now dB is mu 0 by 4 pi I dl. Now sin 90 it was 1, r square was this sin phi. From here these parts are fully constants. So integration of dl, and dl means the whole circular wire, which is 2 pi a. Okay, so now put the value of sin phi. So what is sin phi? As you can see, sin phi is perpendicular by hypotenuse, which is a by r. Sin phi is a by r. So if I put it here, a by r, r is this. So on calculations we are getting this. That means this is our magnetic field due to the whole circular wire along px. Okay, and if I take n turns, now this is the magnetic field. If I take n turns, this is the magnetic field. Clear? This becomes the magnetic field if I take n turns. So this is the magnetic field at the center at a distance x due to the whole circular wire. Clear? Now if the radius is very, very small to the distance from the center, then we can omit a square and we can write it like this. Okay, we can omit the a square and we can write it like this. So please watch here, 4 pi x cube. So in this formula only you can omit the a square. In this formula only you can omit the a square and write it like this. So mu 0 by 4 pi 4x cube. I think there will be a pi here. 2 pi x cube. Okay. Yeah. So please watch here. If I take n turns, then n is multiplied, and this is the formula. And also if a is neglected, a square is neglected, then we can take this. Okay, now NIA is called the magnetic dipole moment. So instead of NIA we put this formula, and here is the magnetic field due to the magnetic moment. So please keep a note of it. This is the magnetic moment. Okay, magnetic dipole moment, as you can see here, M is the magnetic dipole moment of the current loop. And what is the SI unit of M? It is ampere meter square, because it is I into A, so it is ampere meter square is the SI unit of this. So this is the magnetic field due to the circular wire at a distance of x. Please watch here. Next, you have to take a note of this, that if the current enters clockwise through the coil, that end is the south pole. Please watch here. If the current enters, let me show it properly. Suppose in that circular wire the current has entered clockwise, so mind it, that pole will be the south pole. And if the current enters anti-clockwise, that pole will be the north pole. Please keep these in mind. Okay, if the current is entering in any part clockwise, so that pole will be the south pole. And if the current is entering anti-clockwise, that pole will act as a north pole. The Ampere Circuital Law, again a very important topic, Ampere Circuital Law. So what is that? It states that the line integral, so this is the line integral, of magnetic field induction B around a closed path in vacuum, mind it, it is in vacuum. This is a closed path, watch here, this is a closed path, also this is a closed path. So the current in this is flowing like this, and the current in this is flowing like this. So closed path. So magnetic field, there is the line integral of magnetic field induction around a closed path in vacuum is equal to mu0 times the total current flowing through the closed coil. Okay, suppose this is a closed coil carrying current I. So they are telling the line integral of magnetic field is actually mu0 times the current flowing. This is the Ampere Circuital Law. This is Ampere Circuital Law. Clear? So here okay friends, so let's see. So watch here, in this loop the current here is entering clockwise. Okay, the current in this loop is entering clockwise, and in this loop it is entering anti-clockwise. So due to the clockwise, I can tell what is the magnetic field. It will be I1 mu0 I1, and due to the anti-clockwise I can tell the magnetic field will be minus, because the direction is opposite. So due to both the wires, what is the magnetic field? This is the magnetic field. Due to both the wires, the magnetic field is this. Clear? Okay. So please remember, due to both the wires, the magnetic field is this. Next, proof of Ampere Circuital Law. So is Ampere Circuital Law, which is telling line integral of B dot dl equal to mu0 into current. This is the Ampere Circuital Law. So let us see whether it's coming or not. Clear? First, Okay. Proof of Ampere Circuital Law. So suppose this is a wire carrying current. A wire is carrying current in this direction. Clear? From X to Y, and we know that the magnetic field direction will be, using the right hand thumb rule, the magnetic field direction will be like this. Like this. Magnetic field direction will be like this. So suppose at a distance of R from the center at P, what is the magnetic field due to the current carrying conductor? We have already done that. It's mu 0 I by 2 pi r. Mu 0 I by 2 pi r is the magnetic field at a distance of R due to a current carrying conductor. Now, line integral of B dot dl. How to write? Line integral of B dot dl. So, B dot dl, dot means cos theta will come, cos theta will, and what is the angle? Please watch here. This is the B, direction of B, and this is the dl. So dl and B are in the same direction. BL and D are in the same direction. If you can watch it, DL and B, the small element DL and B are in the same direction. So the angle between them will be 0. So it is B dot B dl. Now B is outside, constant, dl and dl will be 2 pi r due to the whole wire. So this line integral of B dot dl, how much did I get? It is B into 2 pi r, and B for a circular wire is mu 0 I by 2 pi r, which is cutting. So we are getting this. That means it's correct that if I want to find out around the closed loop what is the total magnetic field, I can only do mu 0 into I. Mu 0 into I in vacuum. Mu 0 into I. I is the current flowing through the wire. Clear? Next, let's see the next part. Applications of Ampere Circuital Law. Applications of Ampere Circuital Law. So what is the application of the Ampere Circuit Law? It is used to find magnetic field due to current flowing in a closed loop. Please watch it. Ampere Circuital Law is to find only for closed loops. Ampere Circuital Law is only for closed loops, and I will find the magnetic field due to the closed loop carrying current, which I can easily find by using the formula mu 0 I. Clear? So next, okay. So friends, here magnetic field due to a long straight wire carrying current. That was magnetic field due to a wire. That was magnetic field due to a wire. So this was magnetic field due to a wire carrying current. But now we are doing what? Magnetic field due to a long straight wire carrying current. Long straight wire carrying current. Okay. So let us take a long straight wire which is carrying current I. At a distance of R, we see that magnetic field and dl are having the same direction. So theta will be 0. So using line integral of B dot dl, B dl cos 0, so it is B dl. dl, B will be out, dl will be 2 pi r. Total length of the wire will be 2 pi r. But Ampere Circuital Law says that line integral of B dot dl should be mu 0 I. That means this should be mu 0 I. So if this is mu 0 I, we can find the magnetic field. So how easily we can calculate the magnetic field due to a long straight wire, right? Next, the magnetic field due to a infinite straight wire carrying current has a cylindrical symmetry. Please watch. Isn't it looking like a cylinder? Cylinder. See, it is looking like a cylinder. So long straight wire means it will look like a cylindrical thing. The magnetic field, magnitude of the magnetic field increases as the distance from the wire decreases. See, magnetic field is given how much? B proportional to 1 by R. So lesser the distance from the wire, more is the magnetic field. Clear? So let's see the next thing. Now we will do magnetic field due to a current through a very long cylinder. Very long cylinder. So this is the long cylinder through which the current is passing. This is the long cylinder through which the current is passing. So let us see. Let us take the radius of the cylinder as R. Let us take the radius of the cylinder as R, carrying current from X to Y. Now case 1. So see, basically two cases will arise here. One, if the point P is outside the cylinder, and second, if the point P is inside the cylinder. That means here we will take R as greater than R, greater than the radius, because point P outside the cylinder. So line integral of B dot dl equal to mu 0 I, which we know that. So line integral of B dl cos 0, because B and dl are in the same direction, so angle is 0 degree between them. Now Ampere Circuital Law told that it is mu 0 I. So B dl, line integral mu 0 I, and dl is the total length, which is 2 pi r. This is the circle we are choosing at a distance of r. Suppose this is r, so total length will be 2 pi r, which is mu 0 I we are getting. So I will be this. B magnetic field will be mu 0 I by 2 pi r. Due to the whole cylinder outside it, at a point outside the cylinder, magnetic field due to the cylinder at a point outside the cylinder is mu 0 I by 2 pi r. So we can see it is inversely proportional to r. Second, we will take at a point which is inside. We'll take at a point which is inside. So let us see. R will be less than R. Here we are taking the point inside. And remember, this is the radius of the cylinder. So if the cylinder is a sheet and I flows along the surface, please watch one thing. If the cylinder is a sheet, very very thin sheet, and I is flowing along the surface of the cylinder, thin sheet, please remember magnetic field will be 0. Magnetic field in that case will be 0. If it is a thin cylinder made of a sheet, the magnetic field on the surface is 0. Now if the cylinder is a solid object, that means full solid, full solid object, the current I dash along the loop L. So how much current will flow along only this part? We know that for the whole cylinder, if I take a loop this much, the radius, if I take the loop this much, the radius is r, so the area is pi r square, and for the whole pi r square the current is I. So for only this much the current will be this. Because capital I is for the whole area, pi r square. So for only this much area the current will be this. Clear? Cutting, and we got the current is this. Now applying the Ampere Circuital Law, line integral of B dot dl is mu 0 mu r. Now why did we give mu r? because now it is inside, and mu r, it is inside the cylinder, and mu r is called the relative permittivity of the cylinder. Clear? So using this b dot dl, b dl cos 0, we are getting this. So now we are getting this I r square by r square. So we are getting this, yes, correct. So line into B is outside, so dl will be 2 pi r. 2 pi r will be this. Clear? So B will be this. That means this is the magnetic field. This is the magnetic field inside the cylinder. This is the magnetic field inside the cylinder at a distance of r, where mu r is the permittibility of the material of the cylinder. So we can see B is proportional to r. See, if we draw a graph showing the magnetic field with the distance, so we saw that at a distance of r, see, at the center the magnetic field is 0. Now till the radius, till the surface, the magnetic field is directly proportional to r, so it will go rise like this. And outside, the magnetic field's formula was how much? Outside, the magnetic field formula was this. This is the magnetic field's formula outside. Mu 0 I by 2 pi r. So we can see that B was inversely proportional to r. That means if we plot it, see, we are getting this. Here B was inversely proportional outside. That means more at a distance of this is outside the cylinder, and this is inside the cylinder. And this is on the surface. So as we can see there, this is the magnetic field due to the this is how magnetic field variations takes place. Next is we are going to study a topic, solenoid. So what is a solenoid? A solenoid consists of an insulating long wire wound. Solenoid consists of an insulating long wire wound in the form of helix. That means like this. Like this, in which the length, this length is very large than the radius. Length is very, very large than the radius of the helix. Okay. Now we will find out the magnetic field due to the solenoid. So let's see the magnetic field due to the solenoid. So here is a solenoid. Please watch. Here is a solenoid in which the wires are wound like this. Wires are wound like this. Okay. And suppose N is the number of turns per unit length and I is the current flowing through the solenoid. Current flowing through the solenoid is I. Let us choose a part of it. Let us choose a small closed loop so that we can use Ampere Circuital Law. This is the closed loop. So here let us choose the length as L. Okay. So how much number of turns is here? N into L, because per centimeter is N turns. So in the length of L, the number of turns will be taken as NL. So in this case, now watch here please very carefully. We want to apply the Ampere circuital law in the path, closed path. So here we are applying the Ampere circuital law in the closed path. So first it will be P to Q, then Q to R. First is P to Q, then Q to R, then R to S, and then S to P. So 4 parts. So please watch one thing, that in the P to Q, part, the angle with the length of the element and the magnetic field is 0 degree. So we will apply B dl cos 0. In the Q to R, the angle of the magnetic field and length is perpendicular. So B dl cos 90. In the S to R, it is cos 180 opposite, and in the R to S, again it is perpendicular. Direction of B and length are perpendicular. So cos 90 will be 0, so this will be out. This will be out. Cos 180 is minus 1. So this comes. Okay. So now what we can see here, because S to R is outside the cylinder, so magnetic field will be 0. S to R is to outside the cylinder. So we will also not take this part. So we will take only this part. So B is outside and length from P to Q is L. So this is the magnetic field due to the solenoid. Clear? So now watch one thing, that is, if I use Ampere circuital law, we know that Ampere circuital law is given as total magnetic field around the closed path should be mu 0 I. That means BL is mu 0 I. So this is the magnetic field due to the solenoid. Okay. Now here what I can tell, what is the total current? If there are n turns, what is the total current? Total current will be NIL. Total current due to the total length will be NIL, and cutting that we get, this is the magnetic field due to the solenoid carrying current I having n turns per centimeter. Okay, and this is the magnetic field at any one end of the solenoid. This is due to the whole solenoid. This is due to the whole solenoid. Magnetic field is, this is due to whole solenoid. And this is due to at any one end, at a point near the ends. Now what is toroid? Next let us see toroid. What is toroid? It is a hollow circular ring on which a large number of insulated turns of a wire are closely wound. It is an endless solenoid. Please remember, endless solenoid. So it is like a solenoid only. So the magnetic field due to the toroid will also be this. Magnetic field due to a toroid, because it is an endless solenoid. Next, comparison between Ampere's circuital law and Biot Savart law. It's a very important topic, so let's see. Similarities, both relate to magnetic effect of current. Yes, both due to Ampere circuital law and Biot Savart law, we can find the magnetic effect due to current. Both express physical significance of steady current. That means if the current is steady, flowing steadily, okay, we can find the magnetic effect of current due to the flow of the current. Now differences, Ampere circuital law is applicable for symmetrical current distribution. Biot Savart law is applicable for non-symmetrical. So please remember this, current distribution. Ampere circuital law only for symmetrical, okay, and Biot Savart law non-symmetrical. Ampere circuital law is for integral form of B. Integral form of B. And Biot Savart law is the differential form of B. Differential form of B. So these are the differences. So as we have discussed, this is the end of the chapter as we have discussed. So please watch that today we have discussed the whole topic of the magnetic effect due to the flow of the current. Okay, so my suggestion is that please go through it very nicely and please pause the video and listen to my lecture very carefully. Okay, pause it many times, listen to it, keep notes of your own. This is the complete notes what I have made for you. You don't have to make any notes of your own. And if you can completely understand this, then I am telling the numerical part of this chapter will not be a problem to you. So my suggestion is please go through this, study and read and understand the concepts how I have done. So all the type of conceptual questions will come from my notes only. That is enough to study for your boards. So please go through it, study it, and I hope you have enjoyed the video. So if you have please enjoyed the video, please like, share and comment. Please like, share and comment my this particular channel so that I can make more and more videos for you. Okay, please like, share and subscribe to my channel. So till then, it's goodbye from my side till we meet for again another class of physics the next time. Okay, so it's thank you from my side and please keep watching and keep enjoying Parijat sir classes. Thank you so much.